algebraic forms of vectors. So how can we take these arrows and represent them in some sort of algebraic way? Well, there are two forms that we can use. The first one is called component form. Let's take a look here at this vector. I'm going to call it vector A. And let's say that the initial point is the point 3, 1, and the terminal point is the point 7, 3. Well, component form takes a vector and says, what if you could only travel either horizontally or vertically, and you wanted to get from point 3, 1 to 7, 3? How would you do that? Well, of course, you would walk right along here. How far would that be? Well, this must be the point at 3, where x is 3, and this here must be the point where x is 7, so you've obviously traveled a distance of 4. And then from here up to the end of the vector, let's see, notice I've only traveled horizontally 4 spaces. How much would that be? Let's see, this was at 1 on the y-axis, and then that ending point is here at 3, so it looks like I've traveled 2 units upward. Well, we can use those two values, the 4 and the 2, to write down a name for this vector. Here's what we do. We say vector A is, and then we use these arrow symbols, vector 4, 2. The first number is called the horizontal component, and the second number, of course, is the vertical component. In my example, both values were positive because I walked to the right and then up, which are positive directions. If I moved left or down, I'd end up with a negative value. But this is now an algebraic name for vector A. Well, what if I wanted to talk about the magnitude or direction angle of vector A? It would probably be easiest to redraw vector A as a position vector. Remember, I can move it around wherever I want. So I've picked up vector A and I've started it now at 0, 0. Remember, it's exactly the same vector. So I know that I would still have a horizontal component of 4 and a vertical component of 2. Do you see that means that the terminal point, when I draw it as a position vector, is now the point 4, 2. It starts at 0, 0 and ends at 4, 2. When you have a position vector, the numbers in the coordinates of the terminal point will match the numbers in the component form of the vector. So how would I find the magnitude of vector A? Well, that just refers to its length, and I think you can see right in the picture, this is a right triangle, so I could just use the Pythagorean theorem. I'd have 4 squared plus 2 squared equals c squared, using c for the hypotenuse. That's 16 plus 4, which is 20. Square rooting each side and simplifying is going to give me 2 square root of 5, right? 20 is 4 times 5, square root of 4 is 2. So the magnitude would be 2 square root of 5 as an exact answer. Or if I want a decimal, I go to the calculator. I got about 4.47. You can check that. How about theta, the direction angle? Well, we'd be talking about this angle right here. How would I find that? Again, I have a right triangle, so I can easily use trig. Let's see, I should use the values I was given, the 2 and the 4. It would be the tangent ratio that links up those two values. The tangent of that angle would be 2 over 4, which reduces to 1/2. I'm in the first quadrant, so I know I can easily find theta by simply using the tangent inverse function. I am in degree mode here. I would just need to type in inverse tangent and 1/2, and I get around 26.6 degrees. So component form is one algebraic form that we can use. The other one is called IJ form. And let me show that to you. Notice the I and the J are in bold. They themselves are vectors. Vector I is this vector right here. It has a length of 1 and it heads directly toward the right. Do you see that the component form for vector I would be 1, 0? I can see that this terminal point is parentheses 1 comma 0. Since I drew it as a position vector, that means the component form will match that 1 comma 0. Another way you can think of it is we traveled 1 unit to the right and then no units up or down. Vector j is similar. Vector j is the vector that has also a length of 1 but heads straight up. And so here's vector j. Its component form would of course be 0 comma 1. We didn't travel horizontally at all. We only moved up a distance of 1, ending at the point parentheses 0 comma 1. Vectors I and j are examples of what we call unit vectors. A unit vector is simply a vector whose magnitude is 1. In other words, its length is exactly 1 unit. I and j are not the only unit vectors, but they're certainly the most well-known unit vectors. Now, what does this have to do with naming our vectors? Here's that same vector a from the previous example. Remember, it started at 0, 0, and when we made it a standard position vector, it ended here at the point 4 comma 2. Let me add some scale to my picture. So that would have to be 4. Here's 2, 1, 2, 3. And then here's 2 and 1 on the y-axis. Well, every vector can be thought of as the resultant vector of a bunch of I and j vectors. In other words, think tip-to-tail rule. If I start at the beginning of my vector and I put a copy of vector I, and then right after it another copy of vector I, I'm going to put 4 in all. Here's 4 copies of vector I. I'm writing them all out tip to tail. Then here's a copy of vector j. Vector j goes straight up and has a length of 1. And here's another copy of vector j. Well, if I take vector I plus another I, 4 of them in all, and I add in a couple of j's, I get vector a. According to the tip-to-tail rule, right? I just start at the very beginning and I end at the very end. This leads us to the ij form of vector a. I plus I plus I plus I, that's 4i, right? Multiplying a vector times a scalar just gives you a vector that's 4 times as long, vector 4i, plus vector 2j. That becomes the ij form of this vector a. Vector a is 4i plus 2j. We had the component form earlier, 4 comma 2. Now we have this ij form. The two forms are completely interchangeable and refer to the same vector. And you can see, of course, the same numbers are used in both forms. Thanks for watching.